Polar architecture, research into novel tectonics with operational efficiency, durability, and energy systems, seeking to hit net zero. Antarctica is on average the windiest and coldest place on Earth. Tasked to rethink architecture in these extreme conditions, I sought to understand how to design a hospitable place in an unhospitable environment. Currently 30 countries with 80 bases on the virtually uninhabitable continent. It is the fifth largest continent, twice the size of Australia, and the least populated. We were challenged to design the Sanae V set to replace the existing Sanae 4. Located on a cliff's edge 160 kilometers from the ice shelf, we were gifted a strong easterly wind and all-round summer sun, whilst in winter no sun at all. Antarctica isn't short of two things, wind and snow. This causes major problems seen in these images. Snowdrift creates a full-time job shoveling snow off the cliff. However, the chore of then having to shovel additional snow into the smelter to produce water. My conceptual response took the two most abundant resources in Antarctica and utilized them at the core of my design response, turning a problem into a solution through intentional deposition for both insulation and water purposes. The smelter has been redesigned, which sees the lower section channeling snow into a catchment area before it is heated through an array of mirrors, occupancy and electrical resistance heat. The water and warmth is then circulated through and around the building. The next utilization of snow is for its thermal efficiencies. On a detailed level, you can see a ribbed stainless steel profile retaining deposited snow, reducing the rate of heat transfer. This forms the concept, intentional deposition, with an internally located smelter for minimal heat waste and lower labor, whilst an improved insulation thanks to a skin designed to hold the thermal efficiencies of snow. An experiment with that hypothesis of the optimal water temperature sought to provide efficient hydronic heating, whilst another sought to empower the structural qualities of pykrete. The form is raised on stilts to prevent snow buildup and increase lifespan. The cross-section is inspired by an upside-down aircraft wing. The wind accelerates beneath and around the structure, intentionally depositing snow into the smelter and keeping the building firmly on the ground, whilst the hexagonal form provides an optimal volume to surface area ratio. Designed in response to the problems that arose in a meeting with the Sanae crew, 6 principles formed the core of the design response. Insulation was key to material selection. An 8-layer composite blocking water vapor or heat transfer helped the building achieve optimal energy use. The entrance into the building is positioned centrally with a pykrete stereotomic garage which utilizes the waste of timber framing whilst also acting as a cold wall to regulate internal temperature. The spiral staircase leads into the service core, the smelter, hydroponic gardens and water storage at the heart of the building. This translucent circulatory space leads north and south with double volume story, work and living spaces. These double volumes provide a higher volume to surface area ratio. The structure comprises of a steel frame double volume space, served by 2 flanks with a central translucent surface area joining the two, intentionally separating work and living spaces. Zooming in, we find the airlocked, raised axis flooring, plan composite and window details. On the north side, a range of working spaces include lab, communication room, and weather station, as well as a medical facility and gym. Whilst on the living flank, sleeping cabins are ensuite equipped, each having views to the outside, down the passage and up the stairs, leading to an open-plan communal lounge, bar and dining area, with a fully equipped kitchen, freezer and storeroom. Windows are triple glazed argon filled to bring in natural light and external connection. Both these top floors lead out onto the snow smelter catchment area. Airlocks separate the spaces, rightly so because of the snow, but also because it doubles up as a helipad. To support the additional weight of both the helicopter and smelter, the pykrete structure was centrally located. The helipad faces due east, perfect for an interwind landing spot. The airlocks then lead onto the work and live flanks for efficient offloading of supplies and personnel. In conclusion, Sanae V aims to improve on the existing Sanae 4, leaning on both learned principles and novel tectonics to improve operational efficiency, snow management, low maintenance, and better research and development of Antarctica. Thank you very much.